Hey you, it's me. Let's talk about two-pointers. A while back, I had a video about removing duplicates from an array in place. Feel free to check that out if you want to see how we use two-pointers to solve that problem. In that video, I did mention that the two-pointers pattern is pretty vague. It mostly focuses on iterating over a collection and evaluating two or more items from the collection per iteration. I wanted to make another two-pointer video to show a scenario where the two pointers don't tail each other but instead act as boundaries. Let's lay out the problem that we want to solve. Say we had an array of integers sorted in ascending order, like -2, 0, and 1. We'd like to produce a new array containing all the squares of the elements in our original array, also sorted in ascending order. In our case, our new array would look like this: 0, 1, 4. 0 is the square of 0, 1 is the square of 1, and 4 is the square of -2. Once again, the real hints or clues we have to know that we should use two pointers for this problem are: the array is sorted, and we're producing something in sorted order. Generically speaking, there is a notion of order here. Secondly, we'll have a constraint asking us to solve this in O(n) time, so that rules out squaring all the elements and then sorting the array, because sorting will just cost us too much at O(n) log n time. Let's stop and think for a second about the potential values that we get when squaring. Squaring a positive integer will yield an integer of equal or larger size. Squaring a negative integer will yield us a positive integer. That's pretty interesting. That means that the square of a negative integer might not fall at the same index as its negative root. We can see this happen in our example when the square of -2 is +4, and we move it from the 0th place in our array to index 2. Another observation we should call out here is that the smaller the negative integer is, the larger the positive number it'll be when squared. So going by that logic, the smallest potential square in our array will be the closest element to 0, and the biggest potential element in our squared array will either be the smallest negative integer squared or the largest positive integer squared. We can express this in indices, meaning in our array, the smallest negative integer will be at index 0, and the largest positive integer will be at index n-1. We'll take the larger square of the elements at indices 0 and n-1. Since -2 squared is 4, and that's larger than 1 squared, we'll take -2 as the first element for our array of squares. I think we have a pattern forming. Iterate over the array. At each step, compare the squares of the lower and upper boundary values. Pick the largest of the two, and then add that to your array of squares. Let's pause for a minute and chat about our array of squares and how we actually want to add elements to it. We know that the array of squares will be the same size as our original sorted array. So if we wanted to point to different positions within our array of squares, we'll need a third pointer. Remember how I was saying earlier that two-pointer problems can have more than just two pointers? Since at each step we find the largest possible element between our boundaries and then move our boundaries, we're actually producing an array that goes from the largest possible square to the smallest possible square. Because we want to return an array of squares that's in ascending order, we'll actually need to populate our array from the end to the start. We can do this by setting that third pointer I just mentioned to n-1, the length of the array. And after every time we write to our array of squares, we're going to decrease our square index pointer, thus building our array from largest to smallest in ascending order. We can see it happen with this example right here. We have our left pointer and our right pointer. We're going to compare the squared values of index 0 and index 3. Here, index 3 produced a larger square, so we're going to put that in our empty squared array. We're going to move our right pointer and our squared index pointer. Now we compare again our left pointer to our right pointer. This time our left pointer produces the larger square, even though it's a negative number. We add it to the square array, we increase our left pointer by 1, and we decrease our square index pointer by 1. Now let's compare right to left one more time. Once again, left produces the larger square. Let's put that in our square array and move our pointers one more time. And here you'll notice that our right and our left pointer are pointing to the same element. That's okay. We're going to take this element and put it in our array of squares. And look at that, we have it sorted. Now that we got a feel for it, let's go try it out. 977 squares of a sorted array. Given an integer array nums sorted in non-decreasing order, return an array of the squares of each number sorted in non-decreasing order. Notice here what the follow-up's asking. Squaring each element and sorting the new array is very trivial. Could you find an ON solution using a different approach? Oh look, it says an ON. That's the exact type of constraint that we mentioned a two-pointer problem would have to prevent us from sorting, which is the approach we compared our two-pointer to earlier. So let's just jump right into it. Just to make this a little bit easier for us, let's create a variable that holds the length of the array. We'll call it n. Let's initialize our array of squares. This is just the Python way of initializing it with a default value of 0 for the size of n. We're going to create a left and a right pointer. These will point to their respective sides of our nums array. And to help us keep our squared array in ascending order, we can create a third pointer called squared index. This is going to hold our next spot that we'll write to in our squared array. Our while loop is going to run as long as left is less than or equal to right. Because remember, the last element to be evaluated will have both left and right pointing to it. The first thing in our while loop we're going to do is create a left squared variable. And this is just equal to nums index left times nums index left. And then we just do the exact same thing for our right squared value. Our if conditional is going to check if our left squared value is greater than our right squared value. If it is, we're going to add it to our squared array at squared index. And then after we add that left squared value to our squared array, let's increment our left pointer by 1. Our else means that our left squared value was less than or equal to our right squared value. If that's the case, we're going to add our right squared value to squared array index squared index. Then after that's added, we're going to decrease our right pointer by 1, moving the boundary down to the left. Outside the if-else statement, but still in the while loop, we decrement our squared index pointer by 1. Regardless of which squared value we put in the array of squares, we still use that index. So now we need to move one element to the left. Once our while loop has completed, we just return our array of squares. And that was using the two-pointer pattern to make an array of squares from a sorted array. I love this problem. It's a great example of how to not take the two and two-pointers too literally. So remember, we just made a left and a right boundary, we squared the value at each of those boundaries, we compared them, and then added them to a square array. The real trick was just making sure that we were adding things in the correct order in our array of squares, but that was easy once we created that third pointer. As always, thank you so much for coming along. Don't forget to like and subscribe, or leave a comment if there's any pattern, algorithm, or problem on LeetCode that you want to go over. So from me to you, have a great day. Two pointers. 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 So many trucks on this street.